Okay, so we're going to do the nth degree Taylor polynomial of f at c. Okay, so we kind of hinted at this nth degree in the last video. But the nth degree, we go out in terms. So Tn of x is how this is denoted. This is equal to f of c plus f prime evaluated at c over 1 factorial times x minus c to the 1 plus f double prime evaluated at c divided by 2 factorial x minus c to the 2, and then dot 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 all the way out to f to the nth derivative evaluated at c over n factorial x minus c. Let me move this over since I'm running out of room. Okay, x minus c to the n. Okay, now note f of x is equal to the limit as n goes to infinity of Tn of x. So what is this telling me? If I take an nth degree polynomial and I push that n out to infinity, okay, if I take n to infinity, then that is going to go out further and further and further, forever and ever and ever, and I actually get that series n equals 0 to infinity of that f n c over n factorial x minus c to the n. This is my definition of the Taylor series, right? So that's just a concept that if we push it out to infinity, n to infinity, then we get the actual what the function f of x is equal to. Now in reality, we can't do this, but what we can do is we can say, since this is true, then f of x is equal to Tn of x, okay, plus some remainder, okay, plus some remainder, plus a little bit of something else in the dot dot dots, okay, that tells me, that it's actually equal to. Okay, so this right here is the remainder of the Taylor series. The remainder of the Taylor series. So how does the remainder of the Taylor series work? Okay, so if the limit as n goes to infinity of Tn of x equals what? Well, how can I solve for Tn of x here? I subtract Rn from both sides, right? So this is equal to the limit as n goes to infinity of what? F of x minus Rn of x. Okay. If this is equal to 0, right? If this limit is equal to 0, then what does that tell me? Then the limit as n goes to infinity of Rn of x has to equal 0 for x minus c, the distance between x and c, to be less than the r, the radius of convergence, okay? And what else is true? F is equal to the sum of its Taylor series on the interval of convergence. Okay? Pretty interesting fact going on there, right? And this kind of thinking propels us into the last section that we will cover for this textbook, okay? 11.11, which is applications of Taylor series. All right, I'm going to say applications of Taylor polynomials. Okay, so we can use the Taylor polynomial Tn of x equals k from 0. I got to use a different starting letter because I'm going to n. So fk of c over k factorial x minus c to the k, okay, to approximate f of x. Now, it doesn't get us our exact answer because we're not going to n equal to infinity, right? But it does allow us to approximate. That's stopping at the nth degree Taylor polynomial. We can approximate. Now, the question becomes, anytime we approximate, how good is the approximation? How good of an approximation is it? All right, is it a bad one? Is it a good one? How do we know? Well, what do we know? We know f of x is equal to the Taylor polynomial degree n plus your remainder, okay? The remainder is really kind of what we need to look at to figure this out. If we know more about the remainder, then we might know more. So we need to look at the absolute value of the remainder, which is equal to the absolute value of f of x, the distance between f of x, the function, and the nth degree Taylor polynomial, Tn of x. Okay? Now, Taylor's inequality. Taylor's inequality. What is Taylor's inequality? The absolute value Rn of x is less than or equal to m over n plus 1 factorial x minus c to the n plus 1, where the absolute value of the n plus 1 derivative is less than your m, your max value of that function, nth plus 1 derivative there, okay? Basically, this is the n plus 1 term for your Taylor polynomial, okay? So this is the term right after that last one. You think about it, it's exactly like when we talked about the alternating series test. We said that the remainder, the absolute value of the remainder was less than or equal to that a n sub 1, n plus 1 term. This is that an plus 1 x minus c to the n plus 1 term for my Taylor polynomial, okay? That's exactly what's going on there. All right, so I know it's kind of a lot to take in there, a lot of theory going on. But let's see if we can actually work through one example. Okay, so let's see if we can work through an example here. I want to find the Taylor polynomial T3 of x for f of x equals the natural log of x centered at c equal to 1. Okay? Once I do that, I want to approximate f by evaluating T3 of 1.1. Okay? Use Taylor's inequality to estimate the accuracy of the approximation f of x is approximately Tn of x when x is between 0.5, and 1.5. So estimate the accuracy on this interval here, okay? So a lot to take in here. So what I'm going to do, I'm going to shrink this problem up. That way, we can see it for a little bit anyway. All right. So find T3. So what does T3 even look like? T3 of x is equal n from 0 to 3, Fn of, well, where am I centered at? I'm centered at 1. I'm going to put c here for now, over n factorial x minus c to the n. My c is equal to 1, okay? So what is this going to be? So the first derivative, the zero derivative is just the function over 0 factorial x minus c to the 0. And then I have f prime evaluated at c over 1 factorial x minus c to the 1 plus f double prime evaluated at c over 2 factorial x minus c to the 2 plus f triple prime c over 3 factorial x minus c to the 3. That's my T3. Okay? So what do I need to do? I need to figure out what f is. Well, I know that f is equal to what? F of x is ln x, right? Okay. So if I do my little table, okay, so I've got my n equal to 0, my f nth degree derivative, and then my f n evaluated at what? Evaluated at 1, right? So ln of 1 is equal to 0. Next one, n equal to 1. F prime of x is 1 over x. Evaluated at 1 is 1 over 1, which is 1. 2 would be second derivative. The second derivative will be negative 1 over x squared. Evaluated at 1 would give me negative 1 over 1 squared, which is negative 1. 3, that'd be the third derivative. This is positive, what do we have? 2 over x cubed. Don't do that in your head. Write it out. Plug it in, 2 over 1 cubed, which is 2. The fourth derivative would be what? Negative 6 over x to the fourth, which is negative 6 over 1 to the fourth, which is negative 6 here. Man, doesn't look like I'm getting a pattern here, okay? But do we need a pattern? The answer is no, we don't need a pattern, right? We don't have to have the pattern for this one, all right? The pattern's a little bit more challenging, right? So I'm going to simplify this, okay? So this is going to be equal to what? What is f of c? That's 0 over 0 factorial x minus, and I'm going to replace c with 1 to the 0, plus, and then f prime evaluated at 1 is 1 over 1 factorial x minus 1 to the 1, plus, and then I have a negative 1 over 2 factorial x minus 1 squared, and then plus, it's a 2 over 3 factorial x minus 1 cubed, okay? This simplifies. This first term goes to 0. This next term looks like x minus 1. The next term looks like minus 1/2 x minus 1 squared. And the last term is 1/3, okay, x minus 1 cubed. How did I get the third here? Well, I used algebra to simplify, okay? This is 2 over 3 times 2 times 1. The 2's cancel, and I get the 1/3, okay? So this is my T3, okay, my T3. So it looks like I went out just one too far, but in reality, I didn't go out one too far, okay, because we'll use that here in a second. So if you want a T3, go out to at least n equal to 4, okay? So what was I asked to do? Approximate f with T3. So T3 evaluated at 1.1. This is 1.1. Let me do different color here. So let me see if I can plug this in. T3 of 1.1. Okay, so that's 1.1 minus 1, and then minus 1/2 times 1.1 minus 1 squared plus 1/3 times 1.1 minus 1 cubed. Okay, and when I type this in my calculator, let's see, I get like 1/10 minus 1/2 times 1/100 plus 1/3 times 1/1000. This is 0.1 minus 0.005 plus 0.0003 repeating gets me 0.0953 repeating. Okay, so that's my T3 evaluated at 1.1. All right, now what else was I asked to do here? Okay, use Taylor's inequality to estimate the accuracy on this interval here. Okay, so I've just evaluated this function here that gave me a number. I want to know how accurate it is on this interval. What's the max error that might occur, right? Using my T3, which is not exactly equal to f of x, which is the natural log of x. All right, that might be challenging to calculate. Okay, by hand. So what do? I look at the absolute value of R3. Now, R3 is less than or equal to m over 4 factorial, absolute value x minus 1 to the 4th. Okay? Now, what is capital N here? Okay, we got to go back to our formula, right? If it's Rn, that's R3, okay? The third degree Taylor polynomial. 3 plugged into here gets me that 4 factorial. 3 plugged into here gets me that 4 exponent, right? So what's going on? M is the absolute value less than, okay, so what do I have? M is going to be the maximum, right? It's the max on what interval? What interval do I care about? It's the max on 1.5 to 0.5. My function, my fourth derivative obtains. Okay. Now, what does the fourth derivative look like? Well, say I take my fourth derivative here. Okay, the fourth derivative. This is negative 6 x to the 4th. If I graph this, negative 6 divided by x to the 4th, okay? Ooh, what have I done? Okay, so that is my graph of negative 6 x to the 4th. Now, the problem is when I take the absolute value, that negative 6 x to the 4th, or x to the 4th, all of a sudden the negative turns into a positive, right? So this becomes positive 6 over x to the 4th. So that's what I'm looking at, the max value of this, because the absolute value takes care of that negative. So now my function is going to turn into the absolute value of that. So if I want to, I can do absolute value. To do absolute value, go to number, absolute, and then you can type in negative 6. This is kind of overkill. You don't have to do this. You can just type in 6 over x to the fourth, and you're still going to get your same thing. Okay, so this graph looks like from 0.5 to 1.5 looks like it's decreasing as x increases on that positive side there. Okay, so my graph, when I look at it from 0.5 to 1.5, it looks like I'm decreasing, right? So where is this function, the derivative, where is it going to be biggest? It's going to be biggest when x is equal to 0.5, okay? So I want the max value that it can be, all right, on that interval that they gave me right here. So the biggest it's going to be is whenever it's equal to 0.5. So what do? I plug in to my function 0.5 to the fourth, and I type this in, okay? And what do I get? Well, let's see here. Let's do absolute value, -6 divided by 0.5 raised to the 4. I get 96. 96. So this is less than or equal to, well actually, now we're equal to 96 over 4 factorial. And then what is my x value? The biggest one would be when x is 0.5. So absolute value of 0.5 minus 1 to the fourth. So that's 96 over 4 factorial. And then this is like negative 0.5, but whenever I do the absolute value, that's positive 0.5 to the fourth power. Okay, so this ends up being 96 over 4 factorial, and then that's 1 over 16. When I multiply this out, looks like I get 1/4. Okay, so what does that tell me? The absolute value of the remainder, R3, is less than or equal to 0.25. Okay, so what does that tell me? The max error using T3 of x to approximate on the interval 0.5 to 1.5 is 0.25. Okay, so now earlier, do you remember we found T3 of 1.1, and I think we got like roughly 0.0953333, right? So what this is saying is that this answer right here, the most it could be off is 0.25. So plus or minus 0.25 in either direction. Now, to make this error smaller, all we have to do is increase how many terms we have in our Taylor polynomial. And that's not hard to do. If I wanted to get 30 terms out, then maybe I could make this number like 0.00001, which would be really small. Okay, so it just depends on what tolerance level you're willing to be off for your accuracy. Okay, so hopefully this example, and let me zoom out so you can kind of see it in its entirety, clears it up just a little bit. Okay, very complicated, but not something that's undoable. This is the last concept for Cal 2 that we cover. So congratulations, you've made it through a challenging subject. Good luck in your future endeavors.